Hello friends, you are welcome to part 2 of my series, Embedded Design in Electrical Power Domain. We have identified 3 groups of embedded design activities in the previous episode. The 3 groups are monitor, control and protection. Monitor, control and protection. And I had given these 3 examples. In monitor, 2 examples. One was multifunction meter and another was annunciator, whereas this handles electrical parameters, this handles switches, and then control and protection. What we are going to do is, we are going to first discuss at length the monitors. Do you know that we can neither control nor can we protect any equipment without monitoring its specific parameters relevant to control or protection, as the case may be. So control requires monitoring and protection also requires monitoring. That is what it means. And we need to do it with utmost care, because how carefully you do it will give you the results, good or bad. I will now start with the monitoring activity. What kind of parameters do we monitor? Can you believe that whatever we monitor, absolutely whatever we monitor, we have to first convert it into voltage. This is the key to entire activity that you are going to do. First convert that parameter into voltage. For example, when you monitor a switch, even if it has a potential free contacts, we first translate it to logic 0 or logic 1 voltage level. If we measure current, we first pass it through a resistor and convert it to voltage. If we measure temperature, it is also converted into voltage first by what is known as the transducer. So the transducer converts temperature into voltage. This is true with every parameter. So our first priority is to see how to convert various parameters into voltage. Converting a parameter into voltage is not enough. We need to ensure 2 more things. Number 1, that the maximum voltage is restricted to the safe limit of the CPU. And number 2, that the voltage reaching the CPU is always positive. After all, there is a limit to voltage our CPU can safely handle, and the CPU must remain safe always. So let us start with on-off switches. These switches are either potential free contacts or they carry specific DC voltage. Here I have given 4 examples. Here I have a switch connected in this fashion as in figure 1, or it is connected in this fashion as in figure 2. Now suppose switch is open. If the switch is open, then from this current cannot flow like this. So the current will try to flow through this, and CPU does not draw any current. It draws very negligible current into microamperes. So I will neglect that. So the current flowing through R is 0, and therefore voltage drop across R is also 0. So this voltage minus 0 is equal to this voltage. So this is 3 volts, right? So when switch is open, the voltage you see here is 3 volts. So CPU finds a voltage of 3 volts. If I close the switch, then from 3 volts current will flow through resistance, go like this, and here. So these 2 points are at the same potential. This is 0 level, therefore this also becomes 0 level. So the voltage here is logic 0. The capacitor is meant for debouncing activity, which we will see later. Now the switch could be connected this way also. It depends on the situation. So in this case, the switch is connected like this. So if the switch is open, then no current can flow through this, and therefore the voltage across R will be 0. Effectively, CPU terminal is connected to ground through a resistance R. No current through this, so no voltage drop here. So if this is 0, this is also 0. If the switch is closed, then 3 volts reaches directly to the CPU pin. Okay, so logic 0 or logic 1 is handled in this way. Now there is another way in which switches are connected. We call it switched inputs. The input is 24 volts and it is switched. So if this switch is closed, then 24 volt will get applied like this. It will, potential divider is there, R1, R2. So it will be attenuated to a safe value. Let us assume that R1 and R2 are so selected that this voltage is 3 volts when the switch is closed and 24 volt reaches here. Okay. Now if the switch is open, then if the switch is open, then this point is connected to ground through R2. So you get logic 0. So switch is closed, then you get logic 1. Switch is open and you get logic 0. Right? Now there is a small improvement here. Many times what happens when the site is being commissioned, the fellow, the electrician may by mistake connect positive here and negative here. This 24 volt, you see, the 24 plus, instead of coming here, it comes here, and negative comes here. As a result, negative voltage will reach here. It will be 3 volts, okay, but it will be negative voltage. Minus voltage will go to the CPU and hurt the CPU. So how to prevent this? One way was to connect a diode. So negative voltage will never reach here. But then it will not work also. We want it to work and be safe. So we put a bridge rectifier. So if the switch is closed, then 24 volt reaches here. If it is positive, it goes like this, like this, like this. Through R1, R2, develop 3 volts and back. If the technician connects the wrong way, that is a minus here and plus here, then this plus will go like this, go like this, go like this, go like this, and once again vertically downwards. Means plus here and minus here, and it will come back, and it will come back like this, and reach the negative side. So this is a safer version. This is okay, but it's very unsafe, and this makes it absolutely safe. So the potential drop taking place here and here, roughly 1.4 volts in either case, that can be taken into calculation to develop 3 volts here. Okay. Now there is another way of doing it. The other way of doing it is provided optical isolation. So the world, this world from where the switch is coming, that world is completely isolated from my world of CPU. The CPU is on this side, and on this side is the harsh world. So they are separated by this gap. There is no potential connection between these two. Okay, this is a optocoupler. This is the photodiode, and this is phototransistor. This is photodiode and this is phototransistor. So when the switch is open, no current can flow like this. So current will flow through this diode. This diode will throw light on this transistor, and the transistor will turn on, and therefore you have logic 0 here. Now if I close the switch, then these 2 points are at the same potential. This point is shorted to this point. So current cannot flow through diode. Current will flow like this only. If the current does not flow through this photodiode, then it will not be able to send light to the phototransistor, and therefore the transistor will be off. So this provides fantastic isolation. It is a very common way of handling switches. Now if there is a switched input, that is 24 volt is switched through this switch, even then you can similarly have a phototransistor and a light emitting diode. They are built together and they are called as optocoupler. So the way this works, same way this will also work. When you apply 24 volts, it goes like this. Current will flow through this. When will it be applied? When the switch is closed. 24 volts is applied. It sends a current through this, restricted by R. And this throws light on the phototransistor and the transistor turns on, that is logic 0. If this is open, then current cannot flow through this because there is no path for current to flow, and therefore there is no light falling on the phototransistor, and therefore the phototransistor is off. So logic 1. This is how all these things work. Now let us come to something different from switches. We have to handle a repetitive waveform, and from the repetitive waveform we may have to extract a lot of data. Typically we need RMS value, true RMS value, peak value, harmonic components. Whenever a repetitive waveform is not purely sinusoidal, it is shown to contain harmonic components. For example, if the fundamental component, that is the basic frequency of the repetitive waveform, is 50 Hertz, then because of the distortion, it may contain second harmonic, which is 100 Hertz, third harmonic, which is 150 Hertz, and so on. We are going to measure that. Sequence components, that is positive, negative, and zero phase sequence components, I don't expect any electronics engineer to know this. So if they know, it is fine, very good. But if they don't know, it is nothing unusual about this. We will discuss this separately, and when we work on the sequence components. Then you have to measure kilowatts. kVA, kilowatt is kVA cos phi. This is just kVA, no cos phi. This is kVA reactive, power factor, frequency. These are the parameters we are going to extract. And remember, whatever you want to extract, you must first convert it into voltage, right? Done. So we proceed next. As I have said before, whatever parameter you want to monitor, convert it into voltage first. So there is a current transformer and there is a current flowing through this conductor. I want to monitor this current flowing through the conductor. So I pass this conductor through a current transformer, and then it generates a secondary current, which I make it flow through a resistance. So when the current flows through resistance, I get voltage. Then we send that voltage to ADC. That's it. Similarly, if I had to measure voltage, which could be 11 kV, 400 volts, or whatever, we have to bring it down so that it is safe for the ADC or the CPU to handle. So we put a potential transformer here. But friends, this is not going to work. Why? Because this is the waveform. This is the waveform, and this goes to negative side also. So when the voltage negative part comes, whether it is here, negative part, or here it is negative part, your CPU is not going to handle it. ADC is not going to convert it. So what do we do? So we should shift it up, that is, add some DC voltage so that this point gets above zero line. This point goes above zero line. Therefore, the whole waveform will be shifted up, and then it will be positive all the time, and therefore this fellow, ADC of the CPU or ADC of the CPU, will be able to measure it properly. So this we have to do. So in this picture you see that the waveform has been shifted by 1.5 volts. So all the time these arrows are in positive state. So the voltages are always positive, and therefore whether it is here or it is here, this fellow is able to measure the sample levels. So it will read all these samples. Now you may be wondering, what you have to do with sample? You wanted to measure voltage or current, and I am only giving you samples. So how can you know the correct value? What is all this? You have a valid question. A gentleman long ago developed what is known as a sampling theorem. So how does sampling theorem fit into our scheme of things? The sampling theorem states that a continuous time signal, it does not say sine wave or something, it could be a square wave also, that the continuous time signal can be represented in its samples, as we had done just now, and can be recovered back when sampling frequency fs is greater than or equal to twice the highest frequency component fmax of the message signal. So sampling frequency is fs. The highest frequency component of interest, that is the highest harmonic, for example, is fmax. So as long as fs is more than 2 times fmax, I can completely recover all the information about the waveform. I will know RMS value of the fundamental or RMS value of the components. So this sampling theorem is of crucial importance, and you must always pay close attention when you are working with sampling theorem, so that you understand how we are able to get the parameters as required just by samples, not by actual value. Just by sample, I will be able to extract all the relevant value. So here I will be taking these samples, and I will show you how to use the sample values to derive the parameters that we are looking for. Pay attention to this statement. If fs is more than 2 times fmax, then the original signal can be fully recovered from its samples. This is the masterpiece. Because of this, we are able to handle a lot of complex things. So friends, next time I will go into handling sampling theorem. So pay close attention to this, and now the things are interesting, and they are going to be more and more interesting as the time passes. So friends, see you in the next episode. Thank you so much.